The next example we're going to look at is an example that involves a table. And a table, you can have the same information in a table as you have in a complete graph, but it's just a different way of looking at it. So we're going to apply the cheapest link algorithm to this table, but let's first read the problem. It states, a traveling salesman's territory consists of the 5 cities shown on the mileage chart. Boston, Buffalo, Chicago, Columbus, and Louisville. The salesman must organize a round trip that starts and ends at Louisville, his hometown, and will pass through each of the other 4 cities exactly once. So since they live in Louisville, that means that our reference point is going to be Louisville. So I have here reference point Louisville. Here I have my little pictorial. I think especially with the table, a pictorial is really good. So we have Boston, Buffalo, Chicago, Columbus, and Louisville. So we're just going to go ahead and start applying the cheapest link algorithm. What we're looking first is we're just going to look at all the numbers, and we're looking for the smallest number. It doesn't have to connect to Louisville. It may or may not, but the whole idea of the reference point being Louisville doesn't come in until the very end when we already have our circuit in play. So we're looking at all the numbers. I see here that the smallest number is 209. And it's listed here twice because Louisville to Columbus and Columbus to Louisville. So Louisville to Columbus, that is 209. Okay, now we're just going to look for the next smallest number. And I see that the next smallest number is 292. And that is Louisville to Chicago for 292. Now see that what happens is that we have 2 edges coming out of Louisville, so Louisville is now closed. Now when I'm using a table, what I like to do is when a vertice is closed, I like to just block out the remaining values because they are no longer options, which kind of narrows my field. I'm left with a smaller. In your example online, there'll be a table. It's quite extensive, and so sometimes I would print it out and then just take my pencil and kind of just scribble out the ones that aren't remaining. So we're going to move on. 292. Let's go to the next smallest number, which would be 308 in this example. 308 is connecting Columbus to Chicago. You see, if we were to connect Columbus to Chicago, that would it will close the circuit. So that means that 308 is not an option. 308 is not an option. So we're going to go to our next smallest number, which would be 326. 326 would be Columbus to Buffalo. Columbus to Buffalo for 326. That works. And Columbus to Buffalo. And if you see here, Columbus is closed. So I'm just going to erase the remaining values coming out of Columbus because they are not available anymore because Columbus is now closed. Okay, so we're at 326. The next highest, see when we mark it, there's only a few left, and so it's nice, it kind of narrows the field a bit. The next smallest number is 446, going from Buffalo to Boston for 446. And that means that Boston is now, Boston's closed. Right, and so Boston here, Boston, and Boston here. Which means, and if you look here at our picture, every vertice is closed except the remaining 2 that are left open. So now we know it's time to close our circuit. Buffalo to Chicago. And Buffalo to Chicago has a weight of 522. And that is our Hamilton circuit using the cheapest link. Now we just need to do the last step, which is write it with the given reference point starting and ending at Louisville. So if we start here, we're going to start at Louisville, and let's go to Columbus. And that's 209. From Columbus, we're going to go to Boston, and that is 326. From Boston to Buffalo for 446. From Buffalo to Chicago, which is 522. And then lastly, Chicago back home to Louisville, which is 292, for a grand total of 2,236. And that would be the final answer, or the mirror image, which would just be the back. Louisville, Chicago, Buffalo, Boston, Columbus, and then back to Louisville.